In this video, I will analyze the Carnot cycle. It involves an ideal gas that undergoes a reversible and cyclic process. A Carnot cycle consists of 4 steps. First step, from A to B. Isothermal expansion. Temperature is constant. Volume increases. Pressure decreases. And then the second step, from B to C. Diabatic expansion. Q is 0. C to D. Isothermal compression. Temperature is constant. D to A, adiabatic compression. Again, Q is 0 by definition. Alright, I will analyze Q, W, delta U, delta H, and delta S for all 4 steps. First, let's look at this 5x5 table. We can easily fill in some of the blanks. First, let's look at Q. We have 2 adiabatic processes. From B to C, it's adiabatic. From D to A, it's adiabatic. So we can easily put 0 here and 0 here. And then let's look at the entire cyclic process. It goes from A to B to C to D and then get back to A. Because U, H, and S are all state functions, their changes should be 0 in a cyclic process. So we can put a few zeros here as well. From A to B, it's an isothermal process. Temperature is a constant. And for an ideal gas, U only depend on temperature. H only depend on the temperature. So we can put a couple zeros here as well. From C to D, again, isothermal. Therefore, U and H remain constant in this step as well. Now we'll have to analyze all other blanks. First, let's look at this A to B step. This is isothermal step. So how do we compute work? By definition, work equals the integral of negative P external dV. In this case, it's a reversible process. So we just need to integrate negative P dV. And pressure equals nRT over V. Therefore, we can easily put nRT times the logarithm of VB minus divided by VA. That's it. This is the amount of work here. Again, this is isothermal, therefore we can assume delta U is 0 for an ideal gas. Therefore, Q plus W equals 0. We have Q here. How about the entropy change? Again, it's an isothermal process. Temperature remains unchanged. So the entropy change only depends on the volume change. And what we need to do is we need to integrate the exact differential of entropy, ds. And by definition, ds equals dq reversible over t. And dq reversible equals negative dw reversible. And negative dw reversible is simply pdv. So all we need to do is to integrate pdv over t. So pdv over t is nr dv over v, because p over t equals nr over v. So over here we simply have the entropy expressed as this. Just pay attention here, this expression differs from this expression by a factor of t. So once we have this expression completed, we will be able to do C to D step, which is also a isothermal step. But to distinguish from T hot from T cold, I put a subscript here. This is T hot. And then all we need to do is we copy and paste the first row into the third row. Right, so we'll do this. we have to make small changes. Now the temperature is T cold, so I'll put T sub C here for T cold. This is T sub H, that's T hot. And the volume change should be VD over VC. So this is VD over VC here. Now let's look at the adiabatic process from B to C. Q is 0. Now we'll work on delta U first. Delta U is simply CV times delta T. So the temperature change is from T hot to T cold. So basically we just need to use the final temperature, Tc, and minus the initial temperature of the step, which is Th. And we will be able to obtain the expression for delta U. How about delta H? Similarly, we have H depends on temperature only for an ideal gas, but the dependence is different. Delta H equals Cp times the temperature change. Therefore, I replaced this C sub V with C sub P. Again, H by definition is equal to U plus PV. And therefore, we can prove that Cp equals Cv plus Nr. So now we have this two computed. How about the entropy change? For adiabatic reversible process, well, dq reversible is 0. Therefore, ds is 0. So we can put 0 here and here for an adiabatic reversible process. Now we have Q equals 0, delta U is here, therefore W equals delta U minus Q. So we got this two expression here. Exactly same for W, delta U and W, because Q is 0. Now for the D to A adiabatic process, we again can simply copy paste. But this time, from D to A, temperature changes from T cold to T hot. So this time T hot is the final temperature. T cold is the initial temperature. Therefore, we'll have to change the sign here. Now we need to sum up every single column. Over here, this is going to be 0. I will have to prove this VB over VA equals the reciprocal of VD over VC later. And then it's obvious the sum of these 4 terms is 0. The sum of these 4 terms is indeed 0. Now let's look at Q. So it's a bit easier to look at Q. So when we look at Q, we can see that these 2 terms have a common factor Nr, but not only that, they also have another common factor, which is ln VB over VA versus ln VD over VC. We can easily prove that VC over VB equals VD over VA. How? VC over VB, that's the initial and final volume of a adiabatic process. Therefore, the volume ratio to the power of 1 minus gamma is Tc over Tb. That's just T cold over T hot. And T cold over T hot is also Td over Ta. That's the initial and final temperature of an adiabatic step. Therefore, we can write Td over Ta equals Vd over Va to the power of 1 minus gamma. We just proved that Vc over Vb equals Vd over Va. And therefore, if we swap Va and Vc here, we can tell that Va over Vb equals Vd over Vc. Again, Va over Vb equals Vd over Vc. Therefore, we can actually combine these 2 terms as well. It's just because, again, this term, this ln Vb over Va, equals negative ln Vd over Vc. So I'm going to combine these two terms. Nr is a common factor, and actually ln VB/VA is also a common factor. And then finally, we have to use this TH minus TC here. I will use a small font size here. So this is the expression of Q of the cyclic process. What about W? W equals delta U minus Q. So we put a minus sign here. And this is supposed to be a multiplication sign, so I'm going to use a dot here as the multiplication sign. Alright, you can see, although the Carnot cycle is a cyclic process, overall Q is not 0, W is not 0. W is indeed negative. That means this Carnot engine can do work to its surroundings. So let's see, if we use T hat, this is defined to be Q hat here, when the temperature is higher. Q hat divided by T hat equals, over here, Q cold divided by T cold. So this is Q cold divided by T cold. It's Nr ln Vd over Vc, but again, we just proved that Vd over Vc is the reciprocal of Va over Vb. So we'll put a negative sign here. And finally, W here, W. So we're talking about overall work done by the Carnot engine, so it's this part, divided by T hot minus T cold. And then we will find this to be the answer. So if you compare this expression with this two, you will see just the sign is different. How about the Carnot efficiency? When we define Carnot efficiency, remember we need to maximize the amount of work. So it's going to be proportional to work. And then we need to have work divided by Q hot because we want to minimize the amount of heat the hot reservoir provides to the Carnot engine. And therefore, it's going to be very simple work on top. And remember, it's the amount of work on top because work has a negative sign. Now we get the efficiency of the Carnot engine. So in summary, we filled out this 5x5 table. We computed Q, W, delta U, delta H, and delta S for all 4 steps. And also for the entire cyclic process over here. U, H, and S are state functions. So the change of U, H, and S are all 0 in a cyclic process. And then we know adiabatic processes involves a 0 amount of heat. So we put 0 here. We also know that U and H only depend on temperature for an ideal gas. And there's no temperature change in the isothermal steps. So we have a bunch of zeros here. Finally, just because of the definition of entropy is ds equals dq reversible over T. Therefore, we can put 2 zeros here and here for the adiabatic reversible process. And then after that, we need to use the definition of work, negative integral P external dV, to compute this work here. And also for entropy change, we need to use the integral of the Q reversible over T. And then overall, we filled in this 25 blanks. And then we see that the ratio between Q hot and T hot, the ratio between Q cold and T cold, the ratio between work and T hot minus T cold, these 3 ratios are almost exactly the same, except for this negative sign here and this negative sign here. The efficiency of a Carnot engine is defined to be the amount of work divided by the amount of Q hat. And then we have a simple expression here. By just looking at this expression, we know that the Carnot efficiency can never be 100% because Q code is always positive. Now, if you want to, you can fill out this table all by yourself.